So we have our second order differential equation with constant coefficients. And we have our auxiliary equation. We've looked at the case where what's inside the square root is strictly positive. And now we consider the case where what's in the square root is 0 and we get a repeated real root. Okay? In this case, the real root is going to be equal to negative b over 2a. And so we get one solution where m1 is equal to negative b over 2a. Okay? And so that's great. We have a solution to the differential equation. Now, where's the problem? The problem is this is a second order differential equation. So we know we need to have two linearly independent solutions to get our general solution. We only have one. Well, if you have one solution to a homogeneous linear differential equation and you need a second solution, what do? You use the reduction of order method. Okay? And so you'll recall that we've derived the formula for the reduction of order method where we have our differential equation in standard form. Okay? And we've derived this equation to get a second solution, y2, from y1. Okay? This is how we could compute a second solution from a first solution. So putting our general differential equation, we had our general differential equation with a, b, and c. We're going to have to divide by a just to put it in standard form, and so we'll end up getting b over a y prime plus c over a y equals 0. Okay, so basically here goes our p and here goes our q. Okay, and so we plug that into the formula and we have this p is b over a, and we integrate, and notice that for y1, okay, we have the first solution m1x. Well, what is m1? We see that m1 is negative b over 2a, okay, just from the quadratic equation. And so these end up canceling, and you end up with y2 being linearly independent, okay, from y1 and having this form there. So we got our two linearly independent functions, and we multiply each by arbitrary constant and add to get our general solution. And so let's look at a concrete example. We have this differential equation here. The auxiliary equation is this. Okay, again, the powers of m correspond to the nth derivative. Okay, so m squared, there's a 1 there, negative 10 for m raised to the power 1, and 25 m to the power 0, or the 0th derivative. And we factor this and we get m minus 5 squared. That's the repeated root of 5. So what do we do there? Well, we have one solution right off the bat. And, we could go through the reduction of order, but we did it just more generally. And so we know that we just have to multiply by x to get a linearly independent solution from the first. And we have now two linearly independent functions. We add them together and multiply by a constant. And this constitutes our general solution to the differential equation.